Hello everyone. Here I'll be talking about the algorithm that we have developed for automatic detection of bipolar magnetic region from the line of sight magnetograms. As we all know, the bipolar magnetic regions or BMRs are strong magnetic field regions on the sun's photosphere. It is found to be tilted with respect to east-west line. The angle at which it is tilted is called as tilt angle, as you can see as the red lines in the figure. The tilt angle is found to systematically increase as latitude increases. This is the famous Joyce law. Systematic tilt of BMRs are very crucial in backward flight and process, which explains the generation of polar field in the sun and polarity reversal in solar magnetic cycle. This project is divided into three parts. In the first part, we will be automatically detecting the BMRs from line of sight magnetogram. We use the same method as followed by Stenflo and Kosovyshev in 2012. After that, we have to track the detected BMRs. This part of algorithm is heavily inspired from the work done by Jha et al. 2021. After tracking, we try to study how various properties of BMRs evolve over the course of its lifetime. In this project, we will be using the line of sight magnetogram from HMI and MDI. Before getting into algorithm, first we have to address why do we need to track the BMRs. Previously, many work has been done where tilt angle study has been used to explain various processes in the sun. But many of those do not take into account varying morphological and magnetic properties of the BMRs. And one BMR may be counted multiple times. Since each BMR has individual lifetime, different BMRs will have different weightage in the analysis, which can lead to inconclusive results. So it's very important that we track the BMR before the analysis. Now, getting right into the detection algorithm. Once you have a line of sight magnetogram, the first step you have to correct for the projection effects. Once that is done, you are basically looking for local maximas in the magnetograms. This will serve as our region of interest. Now we apply flux balance condition to our region of interest to filter out bipolar magnetic regions. Once that is done, you can store the information into a binary file and extract morphological, magnetic, and positional information of the BMR. Now we are ready for tracking the identified BMRs. But there are few things to be kept in mind before tracking. One, the tracking algorithm should take into account the changing morphology of the BMR. Also, it should take into account any errors in the detection algorithm. Sometimes it can happen that two different BMRs are identified as one, as you can see in this image. So, what can you do about it? Mostly, faulty detection happens towards the limb of the solar disk. So, one thing we can do is to restrict our analysis to less than 0.9 radius of the sun. To ensure that we minimize the faulty detection, we are going to apply morphological operation on the points of the BMR, which is greater than 100 Gauss, to extract the morphology of the BMR, as you can see in this figure. Now, let's see how applying morphological operation affect our faulty detection. So in this case, even though detection algorithm detect it as one BMR, but the tracking algorithm identifies it as two. Once that is done, we can go ahead with the tracking. In the first step, you have to identify the BMR that you have to track. Here, I have chosen to track this particular BMR. Once you have done this, you can extract the binary file for this particular BMR. Then you can calculate the amount of time for the BMR to reach the limb of the sun from the solar differential rotational profile. Let's call this a tracking period. In the next step, you select the very first magnetogram in the tracking period. Then you extract the binary maps of the intended BMR that needs to be tracked and the second magnetogram. Then you differentially rotate the binary map 1 with respect to binary map 2. Once you have done this, you check for the overlap between differentially rotated binary map 1 and binary map 2. If the overlap is greater than 600 arc-second square, we consider the BMR as tracked and the tracking information is stored in a text file. And the tracked BMR is given a unique ID. We have successfully run the algorithm for a period of solar cycle 23. We have identified and tracked for 3,550 BMRs, and we have checked for the evolution of tilt, flux, magnetic properties of all these BMRs. In some cases, we see that there's a strong correlation between how tilt and Bmax evolve, as you see in this case. But there are enough cases in which we don't see such correlation, or in some cases, even anti-correlation. From this, what we understand is that every BMR is different and evolved differently. So each of them has to be considered with utmost care. So all the BMRs that are tracked are grouped into different flags from -2 to 4. -2 is for those BMRs which have been tracked for enough time, but we only have tracking information for less than 5% of its lifetime. -1 is for those BMRs which have lifetime less than 8 hours. This may even include ephemeral regions. Flag 0, 1, 2, 3 is given depending on the evolution of the flux of the BMRs. Consider this line as the lifetime of the BMR. I have marked 20% and 80% of its lifetime with red line. If the maximum flux of the BMR during its evolution fall in the first 20% of the lifetime, then is given a flag 0. If the maximum flux lies between 20% and 80%, then we give it a flag 1. If the maximum flux lies in the last 20% of BMRs, then we give it a flag 2. If the maximum flux is at the last point of the BMR detection, then it's given a flag 3. And flag 4 is given to those BMRs which are either coming from the far side, by which I mean that initial latitude is less than -45 degrees, or going across the disk, the final latitude is greater than 50 degrees. So we can say that the BMRs with flag 0, 1, 2 are the BMRs that has been tracked for its lifetime. Out of the BMRs that are tracked in the solar cycle 23, over 50% of them falls in the category of flag 4. And 30% of all the BMRs are being tracked for the whole lifetime. 1,326 BMRs to be precise. This figure shows the distribution of the BMRs that are identified in each year, and the figure is overplotted with yearly average sunspot number. As we can see, the general trend of our distribution curve from the detection algorithm and yearly average sunspot number matches. With the 1,326 BMR that has been tracked for the lifetime, we can study how tilt and Bmax generally evolves over the course of BMR's lifetime, as you can see in these figures. Here, each dot represents the average tilt and average maximum magnetic field values over each 96-minute bin. Each bar in the gray bar plot represents the number of data points available in each bin. The large amount of scatter towards the right side of the plot accounts for less data points available for these days, as many BMRs live for a short amount of time, moreover less than 6 days. Here, we see that tilt gradually increases in the first 3 days and it saturates after that. But in the case of Bmax, we see systematic increase in its average value till the 6th day. So, to conclude, we have developed an algorithm that can automatically detect and track the BMRs from line of sight magnetogram. The algorithm is time efficient and can track the BMRs with the area above 1000 arc-second square. And the algorithm can be easily incorporated to any other available magnetograms. We have successfully run our algorithm for solar cycle 23, and we have identified and tracked 3,550 BMRs, out of which 1,326 BMRs were tracked for their lifetime. It was found that tilt of BMRs generally increases over the initial days and gets saturated after that. But in the case of Bmax, we see a systematic increase over its lifetime even till the 6th day. Thank you for your attention.